Welcome back to trigonometry. As promised, we're going to be looking at polar equations some more. But now we're going to be really looking at graphs of some really neat polar equations. And so what I'm going to do is, go through an equation, talk about how to graph it, and then start looking at some patterns and symmetries and that kind of thing. And then help you to start recognizing certain common polar equations and their graphs. And there's more than what we're going to go over, but these are some really common ones, and these are the ones you'll most likely to see the most in your exercises and so forth. But there are more than what we'll talk about. Okay. So let's take a polar equation. You're no stranger to these. You've worked with these already in previous lesson. But let's take the polar equation r equals 4 sine theta. And let's see about graphing this. Let's go ahead and let theta be in radians in this case. It could be in degrees or radians, it's up to you. Let's do radians. And to graph this, let's see, we've got to input a theta and see what the r is. So one way to start graphing is to do a chart. Just like you would do an XY chart in algebra class to graph, equation of a line or something. Here we're going to do a theta r chart. And let's go ahead and start with the 0 theta, since 0 is the polar axis. And we'll take it all the way to 2 pi, but let's go by increments of pi over 6. So we'll use a pi over 6. We'll use 2 pi over 6 or pi over 3. We'll use 3 pi over 6 or pi over 2. We'll use 4 pi over 6 or 2 pi over 3. We'll use 5 pi over 6. We'll use pi. Alright, let me do those first, and then we'll do some more after that. Alright, if you put in 0, sine of 0 is 0 times 4 will be 4. Just plugging in for theta. If you put sine of pi over 6, you'll get 1/2 times 4, you'll get 2. Sine of pi over 3, you'll get square root of 3 over 2 times 4. You're going to get 2 square roots of 3, which is roughly 3.5. Sine of pi over 2, you're going to get 1 times 4 is 4. Sine of 2 pi over 3, you're going to get square root of 3 over 2 times 4. So you're going to again get 2 square roots of 3, or roughly 3.5. 5 pi over 6, you're going to get 1/2 times 4 will give you 2. Sine of pi will give you 0, so 4 times 0 is 0. Okay, and let's plot those and see what we got so far. Theta is 0, that's the polar axis. 4 means we're going to go out 1, 2, 3, 4 circles there. Then pi over 6 is here, and we're going to go out 1, 2. Pi over 3 is here, and we're going to go out 1, 2, 3, around 3.5. Pi over 2, we're going to go out 1, 2, 3, 4. Oh, what did I do that for? I goofed. Sorry about that. Hopefully you noticed. Sine of 0 is 0, and then you should have gotten 0 there, Cindy. It's like looking at my graph knowing that doesn't look right. Oh my goodness. Of course I'm not in class, so you can't yell at me. Haha. For making that stupid mistake. There we go. The key is, though, if you make a mistake, catch it before you turn it in. Alright. That looks better. Much better. Okay. Sorry about that. Alright, so we did pi over 2, 4. 2 pi over 3 is over here. We get 3.5. 1, 2, 3.5. 5 pi over 6 is right here, and we go out 1, 2. And then pi is right here, but we're at 0. Okay, so we got some points. But it doesn't hurt to go a little further. We've only gone to pi, so let's go on all the way around and see where that takes us. So let me just do this so I can keep my chart visible with my graphs, because I don't want to keep scrolling up and down. Alright, so let me try 7 pi over 6, 4 pi over 3, 8 pi over 6 or 4 pi over 3, 9 pi over 6 or 3 pi over 2, 10 pi over 6 or 5 pi over 3, 11 pi over 6, and then 12 pi over 6, or 2 pi. And that'd be enough, because then after 2 pi we're just going to be repeating those angles. We're just going to have coterminal angles, so we'll just be repeating things. Alright, 7 pi over 6, you put that in. Looks like you're going to get -1/2, so you get -2. If you put in 4 pi over 3, you're going to get -2 square roots of 3. If you put in 3 pi over 2, you're going to get -4. If you put 5 pi over 3, you're going to get -2 square roots of 3 again. And by the way, that's about -3.5. Just like this was positive 3.5 over here. 11 pi over 6, we got -2. And then 2 pi, we got 0. Alright, let's go and plot those just to see what happens. Well, 7 pi over 6 is right here, but we got -2, which means we have to go opposite. We have to go across the pole and go 2 in the opposite direction. 1, 2. But lo and behold, we've already got a point there. Yeah, so we don't need to do that one again. 4 pi over 3, we're supposed to do -3.5, so go across the pole, opposite direction, 1, 2, 3.5. Ah, we've already got a point there. 3 pi over 2, we got to go across the pole and go -4, 1, 2, 3, 4. Uh-oh, got a point there. 5 pi over 3, got to go across the pole, -3.5, 1, 2, 3.5. Oh, we've already got a point there. 11 pi over 6, we got to go across the pole, do -1, 2. Already got a point. And then 2 pi, we're back to 0. That's 0. Yeah. So that's all we got. Well, it turns out, if you go ahead and, if you were to fill in some of the points in between, like if you were to do, figure out for pi over 4 and 7 pi over 12 and all that, if you were to do more and more points and get a finer picture, you would see that you have a circle here. Now, I'm not very good at drawing these, especially on the computer, but close enough. You actually end up with a circle. Isn't that cool? Well, hey, I think we did one like this in a previous podcast where we converted the polar equation to a rectangular equation. Well, if you have r equals 4 sine theta times both sides by r, you get this kind of deal, right? I think we might have done that actual equation. And then you go do the whole complete in the square thing. So half of 4 is 2, squared is 4. No, we didn't do this equation, we did a different one, but same process. You get a circle with center at 0, 2, which, if we look at this circle, 0, 2, right there's the center, and a radius square root of 4, or 2. Radius 1, 2, 1, 2, and if you go 1, 2, 1, 2, the radius all the way around is 2. So there you go, that is a circle. Pretty neat, huh? Actually, there's a lot you can generalize here. Notice the form was r equals some number times sine theta. That number is going to tell you about the diameter of the circle. In this case, the diameter is 4. And then whether this is sine theta or cosine theta tells you what axis it's sitting on. If this is cosine theta, it's going to sit on the x-axis. If it's sine theta, it's going to sit on the y-axis. Whether you got positive or negative will tell you which side of the axis too. Alright. Actually, let's take r equals a cosine theta and let's play with it. And let's also take r equals a sine theta and play with that. And we'll make some generalizations here about these polar equations. Now, r equals a cosine theta, if you go and multiply both sides by r, you get that. Then if you convert this to rectangular form, you get that. Subtract the AX from both sides. Get that. Complete this work on completing the square. You get that. And then finish factoring when you're doing the completing the square. You get that. Essentially, you've got the equation of a circle with center at a over 2 comma 0, and with radius a over 2. Pretty cool, huh? And then sine theta, do the same process. Multiply both sides by r. Then you got x squared, convert it to a rectangular equation. Follow the same steps, except instead of a minus ax, you have a minus ay. So in this one, it's another circle. This time the center is at 0 comma a over 2, but the radius is still a over 2. So going back up here, 4 sine theta, a is the 4. And since it's sine, your center should be at 0 comma 2, because a over 2 is 2. And then the radius should be 2. And it is. And that's this formula here. Pretty neat, huh? So graphically, r equals a cosine theta, you would see that circle along the x-axis essentially. Diameter of a. And then r equals a sine theta. You can see that circle essentially along that y-axis. Diameter again is a. Okay. Wanted to mention something about symmetry before we move on. I have at least I have 4 more situations to talk to you about, but I wanted to talk about symmetry for a second. If you are looking at your polar equation, and let's say you have a point r theta that fits that equation. If there's a point r negative theta that also fits, then you have what's called polar axis symmetry. So if you know you have polar axis symmetry, you can find points up here on the top half and then reflect across the horizontal axis to get the bottom half. That's kind of like having x-axis symmetry. If you have an equation with a point r theta that works, if you're able to take negative r negative theta and that work also in the equation, then you have theta equals pi over 2 symmetry. Or basically y-axis symmetry. And if you have the point r theta And if negative r comma theta will work, then you have pole or origin symmetry. Long story short, if symmetry test passes, it has that kind of symmetry, which can really save you a lot of time when you're graphing, because if you know it has symmetry, you only have to get like half the points, and then you can do your reflecting or or whatever. Apply the symmetry to get the other half. If it fails the symmetry test, may or may not have that symmetry. So failing doesn't automatically rule it out. Passing definitely rules it in, having that symmetry, but failing, it still could have that symmetry. You really don't know until you really start graphing it and picking points. But that could be useful down the road. Okay, let's go ahead and graph another one. Let's take the equation r equals 1 plus cosine theta and graph it. Let's see, if we replaced theta with a negative theta, that would still equal 1 plus cosine theta. So this tells us that it has polar axis symmetry. That's like the x-axis symmetry. If we replaced r and theta with a negative, it does not work out the same as the original, so it may or may not have y-axis symmetry. And if we just replaced r with negative, that does not come out the same, so it may or may not have pole or origin symmetry. Okay, but it definitely has the polar axis or x-axis symmetry. Alright, let's do a table. Do a theta r table. Let's see, if theta is 0, plug that in, you'll get 2. If theta is pi over 6, plug that in, you'll get around 1.9. If theta is pi over 4, plug that in, you'll get around 1.7. If theta is pi over 3, plug that in, you'll get 1.5. If theta is pi over 2, plug that in, you'll get 1. If theta is 2 pi over 3, plug that in, you'll get 0.5 or 1/2. If theta is 3 pi over 4, you'll get around 0.3. If it's 5 pi over 6, you get around 0.1. And if it's pi, you'll get 0. We can actually stop there because we know about the symmetry. Alright, 0, 2. Down the 0 line, go out to 2. Here you go. Pi over 6, we're going to go out to 1.9. Pi over 4, we're going to go out to 1.7. Pi over 3, we're going to go out to 1.5. Pi over 2 will go out to 1. Two pi over 3 will go out to 0.5. 3 pi over 4 will go out to 0.3. 5 pi over 6 will go out to 0.1. Then pi we go to 0. And then since it has the polar axis symmetry, we can just reflect across the polar axis there. Zeros stay the same, but we know we're going to have this here, this here, this here, this here, and then this here. And here. So we're going to get this shape. Looks like this. Okay. And what we have here is something called a cardioid. Which is a type of limosone. Looks like limicon, but I've seen the pronunciation in the books say limosone. So there you go. It's a type of limosone. Well, it turns out you've got a equation here of the form r equals a plus b cosine theta. If you have equations of that form, or replace that with sine, then you have these limosomes. You can have r equals a plus b sine theta. You can have r equals a minus b sine theta. You can have r equals a plus b cosine theta. You can have r equals a minus b cosine theta. And all of these, a and b, are greater than 0. If the ratio of a over b is less than 1, your limosone is going to look something like this. It's going to have this little loop. If a over b equals 1, you'll have the cardioid, which just basically looks like a heart. If a over b is greater than 1 but less than 2, we have one with a little dimple, not so much heart-shaped. And if a over b is 2 or bigger, it'll be kind of flat there. It's almost like a tomato. Tomato without the stem. So it won't dimple in. It'll be kind of flattish there and round everywhere else. But those are all examples of limosomes. Yeah, with the cosines, you'll see those along the x-axis, if you will. And with the sines, you'll see those along the y-axis. Plus will be up top, or like plus here, you'll see it on the right. Minus, you'll see it over here on the left. Plus here, you'll see it up top. Minus here, you'll see it on the bottom, like that. So the plus and minus tells you the location. Cosines will be along the x-axis, sines will be along the y, and the plus or minus tells you which side of the axis you'll see it on. And then the ratios of a and b tell you the shapes. Now you don't have to necessarily memorize those shapes. You could just do, enough values on a chart and your shape will come out. But it's really helpful to know what the shape should be, so that way you know, like if maybe you didn't do enough points, you'll still know exactly how it's supposed to look when you sketch it. So it's good to be familiar with these things. Okay, let's do next one. Ooh, let's go ahead and go on and do the flowers. Those are so pretty. I like them. Let's go do those next. The roses and with the petals. The equation I'm going to do right now is r equals 3 cosine 2 theta. Still another polar equation. And you can go through and test for symmetries. If you do r equals 3 cosine of 2 times negative theta, you'll end up still with 3 cosine 2 theta. That checks out. So it has polar axis symmetry, for sure. If you replaced r and theta with negative, that one doesn't work out, so it may or may not have the theta equals pi over 2 symmetry, the y-axis symmetry. And if you replace them both r and, or if you replace just r with negative, yeah, that one doesn't come back to the original either, so may or may not have pole symmetry, or origin symmetry, if you will. Okay, let's do a chart. R theta again, just like we did in the previous example. If you put in 0, you're going to get 3. If you put in pi over 6, you're going to get 3 halves. If you put in pi over 4, you're going to get 0. If you put in pi over 3, you're going to get negative 3 halves. If you put in pi over 2, you're going to get negative 3. If you put in 2 pi over 3, you're going to get negative 3 halves. If you put in 3 pi over 4, you're going to get 0. And if you put in 5 pi over 6, you're going to get 3 halves. And then if you get to pi, you're going to have 3. And that's all we really need, because knowing it has the polar axis symmetry, the x-axis symmetry, we can plot those points and then do some reflecting. That'll work for us. All right, r is 0, we're going to have 3. 1, 2, 3. If you try to reflect, you're still going to be there, so no reflection point. Pi over 6, you're going to have 3 halves. So at pi over 6, you're going to go out 1.5. But that means you can also reflect over here at 1.5. Pi over 4, you're going to have 0. That's right here. Reflecting, you're going to still be 0. Pi over 3, you're going to have negative 3 halves. So you're going to have to go backwards 1.5. But hey, if you reflect, you're going to be up here. There you go. Pi over 2, you're going to end up at negative 3. So here's pi over 2, but you have to go backwards 3. But hey, if you reflect across, you're going to go up here too. At 2 pi over 3, you're going to have negative 3 halves. So here's 2 pi over 3, but you're going to have to go this direction 1.5. But hey, you can reflect across and end up here. Then 3 pi over 4, you're going to be at 0, which you already got a 0. Okay. 5 pi over 6, you're going to have 3 halves. So you're going to be here. But then you can reflect across, and you'll be here. I do double check, make sure I didn't forget anything so far. Okay. And then for pi, you'll be at 3. 1, 2, 3. That's it. Okay, it turns out, right now, I think these just look really cool right now. And if you did some more points, we're not going to do more points because I already know what this shape's going to be. But if you did more points, you would see this. But the shape is a 4-petaled flower. Drawn, sketched basically like so. Again, if you found more points, you would see it even better. Like the points would lay out the flower nicer. But I already know it's a flower, so I'm not going to worry about finding more points right now. Those are significant, those are sufficient key points for drawing my flower. But there it is. If you don't believe me, you can put it in your calculator and check it out. R equals 3 cosine 2 theta. Let's see here. Hit graph. Isn't that pretty? Zoom in to enter. Yep. Yeah, there it is. There's our flower. Isn't that lovely? Isn't that exciting? I love these graphs. They're so much fun. All right, so there's our flower. Well, it turns out you can have, these are called rose curves, and you can have all kinds of numbers of petals, and you may not have them necessarily oriented just like this. To me, that looks kind of like a poinsettia or something, just in time for Christmas this year. As I'm recording this, we're coming up on Thanksgiving and then Christmas soon, but you know, forgive me those of you who are listening to this in the springtime, or summer, but hey, Christmas in July, you know, whatever. All right, but this is a rose curve. If you have a polar equation of the form r equals a sine in theta, or if you have r equals a cosine in theta, where a is not 0, then you've got a rose curve. If it is even, you're going to have 2 times n petals. So whatever n is, it's going to be twice that for the number of petals. If n is odd, you'll have n petals. And they're all going to be spaced apart equally. And once again, like if it's cosine, one of your petals is going to start out on the x-axis. It's kind of cool that way. If it's sine, one of your petals is going to be situated on the y-axis. But let's go back and look. We had r equals 3 cosine 2 theta. We had a cosine. The n is 2. N is even. So if n is even, you're going to have twice that number of petals. Well, if n is 2, we're going to have twice that, which is 4 petals. And we did. And the 3, which in the formula is the a, the 3 tells you where the tips of the petals are going to be. It's cosine. Your first petal is going to be situated here on the polar axis. If you go out 1, 2, 3, there's the tip of your petal. All 4 petals are spaced equally apart around the circle. At the tips of each petal are out 1, 2, 3. 1, 2, 3. 1, 2, 3. Isn't that neat? Yeah, I think I had goofed a little bit when I was trying to reflect that one right there. Because I thought that, yeah, that petal's supposed to be a little thicker. But there we go. But there you go. Those are rose curves. All right, and one more fun one. One more fun one is called a limnoscape. If we start with the equation r squared equals 4 cosine 2 theta, this looks like half of a rose curve when we do it. And really, if you look at the rose curve formula, it's r equals a sine in theta or r equals a cosine in theta. We've got r squared equals a cosine 2 theta, 4 cosine 2 theta. With the limnoscates, you're going to see 2 theta here. And then this is in the form of a squared. So it has some interesting things going on because of this square. So it looks kind of like the rose curves, but like half the rose curves. It looks more like propellers. But anyways, let's do a chart. I'm eager to do this one. I love these. Let's do a chart here. Let's see if theta is 0. You got cosine 0 is 1 times 4 is 4. But that means r squared is 4. So for r, we got plus or minus the square root of 4, which will be plus or minus 2. So at theta is 0, we've got not only positive 2, but negative 2. See that? Whatever this is, the square root of it is going to show you the tips of the limnoscate, the propellers, or whatever. Flower petals, whatever you want to call them. Alright, let's try pi over 6. If we do that, we end up with cosine of pi over 3, because 2 times pi over 6 is pi over 3, times that by 4. We're going to get plus or minus the square root of 2. So basically plus or minus 1.414. Okay, so at pi over 6, about 1.414 roughly. But we've also got negative 1.414, so. At pi over 4, we're going to get 0. Woo. Square root of 0 is just 0. So pi over 4, we got 0. So we got to make sure we have a dot there. Pi over 3, you're going to get plus or minus square root of negative 2. That's not going to work for us. Not going to work. It's imaginary. And then try pi over 2. You're going to get plus or minus square root of negative 4. Not going to work. Alright, so I'm not getting very many points so far, but you know what? Not a big deal. You can either do more values or think about your symmetries. Let's see, polar axis symmetry. I'm testing for that. R squared equals 4 times cosine of 2 times negative theta, which equals 4 cosine 2 theta. It has that symmetry. Very cool. So if it has that symmetry, x-axis symmetry, like if you have this point here, you can reflect across the x-axis and also put it here. Or if you have this point here, you can reflect across the x-axis and also put it here. See how that goes? And then theta equals pi over 2 symmetry. That's basically y-axis. Replace r with negative r. Replace theta with negative theta. And you get back the same equation again. Yay! So it has that symmetry. So if it's on the right, it can reflect across the y-axis and be on the left, but each of our points is already there, so nothing additional for it to help us with that. And then for pole symmetry, just replace r with negative r. It comes back to the original equation. It works, so it has pole symmetry, origin symmetry. So, if you have pi over 6 positive 2, then you should also have 7 pi over 6 2 over here. And you do. Like, looking across the origin, you've already got those points. Alright, well that's all the points we're going to get for now, but you know what? I recognize this formula as being that of a lemniscate. And what happens when I complete the curve is it looks kind of like those rose curves with 2 petals instead. Or you could picture being at the skating rink and doing skating a figure 8. But there's your lemniscate. Doesn't that look cool? Brings back memories of kindergarten. We used to have skate nights at the local skating rink. And I used to like to hang out in the middle of the skating rink and do the figure 8s they had on the floor. Alright, lemniscates. If you have r squared equals a squared sine 2 theta, in that case, your lemniscate is going to be situated like so. And the length of the petal is going to be a. If you have r squared equals a squared cosine 2 theta, your lemniscate is going to be situated like so. And again, the length of the petal is a. So in this case, 4 was the a squared, so a is 2, so the length of our petal was 2. And since it's cosine, it's situated along that x-axis. If it had been sine, it'd be situated at an angle. You can put it in your calculator too if you want. If you don't believe me, check it out. 4 cosine 2 theta. 4 cosine 2 theta. Graph. Oops. Sorry, didn't finish it. That's for r squared, but we're trying to do r. So we have to do plus or minus the square root. So let's see here. Let's insert square root. And then at the end, close in the parentheses. Alright, whatever. Is it going to freeze up on me? Seriously? Looks like it did. Poor calculator. It's had enough for the night, I guess. Okay, let's see. I'm going to temporarily pause and go get this restarted. Okay, I'm back. I had to pause for a second and restart it. Okay, so we got 4. Let me just clear this. We're going to have 4 cosine of 2 theta. Let's hit graph. That's just if you were doing r. But with the lemniscates, we're doing r squared. So what we got to do is the square roots. We're going to say square root of 4 cosine 2 theta. And then we also have to do the negative square root of 4 cosine 2 theta. And then hit graph for that. And you're not seeing it very well. So let's zoom in. Let's try number 2 just see what happens. And oh, these lovely calculators. You gotta love the pixel problems. It doesn't finish drawing this in with its pixel issues, but you know what it's supposed to look like. You know it's supposed to be completed and be this nice figure 8 kind of thing. But there it is. You can also put them in your calculators. Isn't that cool? Well, I'll leave you now to go practice. Graph, graph, graph. Get used to the forms. Be able to graph these by hand. And have lots of fun with getting these images. Now, again, these aren't the only polar graphs. You know, if you do some searching on Google or something, start searching polar equations in their graphs, you'll see a ton more. A really cool site. I don't know if you guys have checked it out, but Wolfram Alpha. If you've never checked that out, I encourage you to check it out. If you go to Wolfram Alpha or Wolfram Math World, Wolfram Math World is the site. It's got a lot of cool stuff, and they have Wolfram Alpha, which is essentially like a calculator. You can download this on your phone too, and you can do all kinds of math with it. But Wolfram Math World, they talk about all these different polar graphs there. They have pictures and equations and all kinds of stuff. So that might be a cool resource to check out. All right. Well, thank you for joining us, and I look forward to seeing you again soon.